Welcome back to Statistical Methods. This is Week 9, Lecture 1, where I will be continuing to cover independent samples t-tests. So just some announcements to start off. Quiz 3 is live today, October 19th, and is due Friday, October 23rd at 11:59 p.m. And also Homework 4 is now live on my Stat Lab, and this is due next Monday, October 26th at 11:59 p.m. So I'm going to start off with a little recap. So last week we learned that an independent samples t-test allows us to test whether scores taken from two separate groups of participants differ from each other on average. So remember that the way in which these two groups differ is our independent variable. And the thing we're measuring and comparing between them is our dependent variable. So for example, if I ask the question, do people remember better when trying to recall information in the same location where it was learned? Our independent variable would be the location of recall. Whether it is the same as where it was learned or in a separate location. And the dependent variable would be the amount of information recalled. So this is the variable we measure and calculate a sample mean from and compare our two groups on. So last time we began walking through the steps required to figure out the characteristics of the null comparison distribution for this test, which is a distribution of differences between sample means, since we're ultimately trying to figure out whether one sample mean significantly differs from another. And we assume that the null distribution is centered on a mean of 0, reflecting no difference between these two sample means. So what is the standard deviation of this distribution? So remember that we can assume that the variability between our two populations of interests are about the same. And this is the homogeneity of variance assumption. Thus, we begin by getting to the best estimate of this shared population variance that we can, known as S squared pooled. And the steps are pretty simple. Step 1 is to calculate S squared for each group separately, using the formula sum of squares divided by degrees of freedom, remembering that each group now has its own degrees of freedom equal to the sample size in that group minus 1. And then we weight each group's variance by its contribution to the overall degrees of freedom to get S squared pooled. So df1 in this formula and df2 are the degrees of freedom from each group, so n1 minus 1 and n2 minus 1. df total is the total sample size, so big N minus 2. So that's the sample size across these two groups, minus 2. And S squared of 1 and S squared of 2 are the estimated population variance that we've calculated from each of these samples. So I want you to open up the spreadsheet independent samples t-test on Blackboard or Canvas. And this contains data from two samples, one with a sample size of 20 and the other with a sample size of 30. And then I want you to begin by calculating an estimate of the population variance for each of these samples in the same way that we did for a one sample and dependent samples t-test. And then using these, calculate the pooled estimate of population variance using this formula here. df1 over df total multiplied by S squared 1 plus df2 divided by df total multiplied by S squared of sample 2. So I would pause the video here and try to do what I just said, so calculating that S squared pooled before listening to this part of the video where I'll go through how you do it. All right, so the first step here is to calculate your mean for sample 1. And if you look up in this portion of the screen, you can see the formula I'm using. So here in I1, we're looking at the average for the range A2 to A21, which will capture sample 1's range of scores. Now, the second step is to calculate the mean for sample 2, which is the average of D2 through D31. So that's D2 here, all the way to D31 here. And the next step is to calculate the sum of squares for sample 1. So do this as you've done before. subtract the mean of sample 1, which is in I1, and don't forget your $sign, from every score in column B, or in column A, rather. Here's your formula. And your degrees of freedom for sample 1 is 19, because we had 20 subjects in this sample. So 20 minus 1 equals 19. And now calculate S squared for sample 1, so that unbiased estimate of population variance based on sample 1. So this is simply your sum of squares from sample 1 divided by its own degrees of freedom. So I4 divided by I5. Next, you're going to do the same for sample 2, sum of squares, degrees of freedom, which in this case is 29 because we had 30 subjects, and S squared. Now, your total degrees of freedom is the entire sample, so between these two groups, which is 20 plus 30 minus 2 equals 48. Now you're going to want to calculate your weighted S squared for sample 1. So that is degrees of freedom for sample 1 divided by total degrees of freedom. Make sure your parentheses look like this. Multiplied by the value in I6, which is S squared for sample 1. And in this cell, you want to do the same for sample 2. And then finally, to get your S squared pooled, add those two values together. So that would be I14 plus I15 to get your pooled variance. Now let's move back to the PowerPoint slides. So, as we saw, sample 2 has 29 degrees of freedom, while sample 1 has 19. Now, because sample 2 accounts for a greater proportion of the total degrees of freedom, we would expect that the final pooled estimate be slightly closer to sample 2's estimate than sample 1's estimate, because it has a greater weight here. Now, is this what we find? Sample 1 found an S squared of 5.29 with 19 degrees of freedom. Sample 2's estimate was 4.01 with 29 degrees of freedom. And our final sample size was 4.51, which is much closer to sample 2's estimate. So our pooled variance of 4.51 is closer to sample 2's because sample 2 has a larger sample size. Now, a simple average of these two variants would give us this here, which is a biased estimate because it's not weighting each of these estimates on a basis of sample size. Now, the next step is to figure the variance of each of the two sampling distributions of means. Now, S squared pooled is now our best estimate of the population variance for both of our populations of interest. Thus, we will now use this to get the variance of the two sampling distributions of means. Now, note that unlike population variance, these two numbers are not expected to be the same because they depend on each group's sample size. So to find that variance of the sampling distribution of means for sample 1, we take our S squared pooled and divide it by the sample size from N1, which is 20. And to do the same for sample 2, we take our S squared pooled again and divide it this time by the sample size for group 2. Now previously, this estimate of the variance of a sampling distribution of means was for a single sampling distribution, and the estimate was based on the single S squared based on our sample. Now we have two sampling distributions of means, and the estimate is based on this pooled variance estimate for both of those sampling distributions. So let's move back to the slideshow, or rather the Excel spreadsheet, to calculate these two values, these variances of our sampling distributions of means. So in this cell here, I19 is where I calculated the variance of the sampling distribution of means for sample 1. And I did this by taking the pooled variance divided by the sample size of sample 1, which is 20. So equals I17 divided by 20. And then I did the same for sample 2, except this time I used sample 2's sample size of 30, so I17 divided by 30. So the variance of the first sampling distribution of means is 0.226, and the variance of the second sampling distribution of means is 0.150. Now we've estimated what our two individual sampling distributions of variances should be. Rather, our two sampling distributions variances should be. But remember that what we ultimately care about here is not these distributions, but a distribution comprised of differences between sample means taken from these two distributions. Now, to figure the variance of the distribution of differences between means, so S squared difference, we simply add up the two individual sampling distributions' variances. This is because in a difference between two numbers, the variation in each contributes to the overall variation in their difference. So here's the formula for that. And to do this in your spreadsheet, you're simply adding the values in I19 and I20 to find that S squared difference. Then just take the square root to get the standard deviation of the distribution of differences between means, so S of difference. And you can do that in Excel by simply raising your S squared difference to the 0.5 power. So these are the two values you should have gotten. So here's a roadmap for getting to the standard deviation of the comparison distribution. Number one is to estimate population variance 2 times, one based on each of your two groups to get S squared of 1 and S squared of 2. Next, you figure the pooled estimate of the population variance using this formula here. 3, figure the variance of each sampling distribution of means by dividing the S squared pooled by each of those individual sample sizes. You figure the variance of the distribution of differences between means by adding these two values together. Then you figure the standard deviation of the distribution of differences between means by taking the square root of S squared difference. Now, the shape of your comparison distribution, which you will use to determine your cutoff values for rejecting the null or not, is a t-distribution with a degrees of freedom of n minus 2, so the total sample size minus 2. So in our sample with 50 subjects, our comparison distribution will be a t-distribution with 48 degrees of freedom. So why a t-distribution? Well, this is still based on an estimate as opposed to a known population variance, as with a one sample t-test and a dependent samples t-test. Now all that's left is to calculate the actual t-statistic based on our data. And we accomplish this by taking the difference between the two sample means and dividing by the standard deviation of our comparison distribution. Now let's go ahead and calculate that for the observed data. So right here, this should be I1, which is the sample mean of sample 1, minus I2, sample mean of sample 2, divided by the standard deviation of the distribution of differences between means, which yields a t-value of negative 0.298 or negative 0.30. So we end up with that negative 0.30. Now imagine we were testing a non-directional or two-sided hypothesis at that 0.05 significance level. Then we would end up with a cutoff score of t equals plus or minus 2.01. We could find that out from the Shiny app. So our t-value is much smaller than that, so we would fail to reject the null in this case. Now, Cohen's d is the typical effect size reported for an independent samples t-test. And it's calculated as the difference between the two sample means divided by the pooled estimate of the population standard deviation. So here's your formula. And this tells us how far apart our two sample means are in standardized units. So in that pooled estimate of the population standard deviation units. So in this example, we just worked through, here's mean 1 minus mean 2 divided by standard deviation, the pooled standard deviation. And it leads to a Cohen's d of negative 0.08, which is very small. So one thing to note here is that you would likely not have calculated the pooled standard deviation while running through the steps for an independent samples t-test, only the variance. So do not forget to take the square root of this number for the calculation. So how do we interpret this? So interpreting the practical magnitude of how big an effect is for a Cohen's d is context sensitive. So it might be deemed a small effect in social science research could have been a substantial effect in, say, medical or pharmaceutical research. Nonetheless, Cohen in 1988 offered the following rough guidelines for interpreting Cohen's d that are still used by researchers today, for better or worse. And Cohen said that a Cohen's d of 0.2 is a small effect, a Cohen's d of 0.5 is a medium effect, and a Cohen's d of 0.8 is a large effect. And again, this is in terms of standard deviations. Right, so this is characterizing the difference between these two means in standard units. So if I ask you in the future to interpret the effect size, Cohen's d, from your study, what I'm asking you for is the following two pieces of information. Whether it would be considered a small, medium, or large effect based on these cutoffs, and the number of standard deviations apart. So if you calculated a 0.6 for your study, I'm looking for something like, this indicates that our two group means were 0.6 standard deviations apart, a medium effect size by Cohen's conventions. So that's all for today, and we'll be back with part 2.